So yeah, hello everyone. My name is Sarah. I'm going to be talking about faer, which is a linear algebra library for us. This is not going to be a very technical talk. So there's not going to be a lot of math or a lot of code. I'm mostly going to be presenting the library and talking about the kinds of optimizations that I did to achieve the performance that I ended up with. So a little bit about myself. I come from a data science background. I started working I first started working with Python, then moved on to C++, and then about 2 years ago, I switched to Rust. And um, I did a PhD for about 2 years, but then ended up quitting because it wasn't really for me. But I still like work on the stuff that piques my interest in my PhD. So that's mostly dense linear algebra and numerical optimization with some focus on sparse linear algebra, in particular sparse matrix decomposition. So faer-rs is a collection of traits for linear algebra with a focus on high performance and portability and correctness, of course. So the library is split into multiple modules. First, you have the core module, which has the foundational stuff like matrix multiplication and triangular matrix operations, like the matrix, triangular matrix solve, and the inverse, as well as stuff like the permutations, the household reflections, the Jacobi rotations, and other things that are used in other modules. You have the classic decompositions. The three main well-known ones are the Cholesky decomposition, the QR decomposition, and the LU decomposition. And the eigenvalue solvers, which are the singular value decomposition, and then the Hermitian and non-Hermitian eigenvalue decompositions. So why make a new library rather than contributing to existing ones? Well, first of all, let me talk about how the ecosystem for us looks like on the linear algebra side. We have two main libraries for large scale linear algebra, which are NAlgebra and NDRA. So NAlgebra is the well-established standard for us currently. It's very well optimized for small matrices, and it has a very convenient API. It suffers a bit when scaling to large matrices because it doesn't explicitly use multi-threading. So the whole library is single-threaded. There's no blocked algorithms, so the algorithms operate on the matrix column by column or row by row rather than in chunks, which is something that can be used to significantly improve the performance. And it doesn't explicitly use SIMD instructions in many places. I know that they are used for matrix multiplication in the matrix multiply backend, but I'm not aware of it being used anywhere else in algebra. And the other one is in the array, which uses the matrix multiply backend as well for matrix multiplication, but for other stuff, it mainly defers to LaTeX. So LaTeX uses OpenBLAS or MKL or something else under the hood. And this is good and bad. Good because you inherit all the robustness and performance that have been accumulated over decades of work on LaTeX. But it's also bad because you have like issues with portability, as well as you can end up with linking problems if you try to use OpenBLAS and MKL at the same time, for example, which is something I ran into on a couple of occasions. And it's also only implemented for the, so to speak, native types. So the floating point types and the complex and the corresponding complex types. So if you have something like, say, a multi-precision number, then you can't use it with existing algorithms, even though the code will mostly be the same. And you also have no fine control over multi-threading. So either the whole application is single-threaded or the whole application is multi-threaded. And it's pretty hard to change the threading at runtime, because essentially that's the way it was done for decades, and it's pretty hard to switch away from that model. So like I said, why not contribute to an algebra, for example? The reason is that to achieve the flexibility and degree of performance that I aim for, it will require significant API changes, mainly on the SIMD side and the multi-threading side. So for vectorization, and algebra doesn't offer a very convenient API for multi-threading for non-native types, which makes porting some of the, which makes writing generic vectorized code quite a bit difficult. And it also doesn't offer multi-threading support. So the code is entirely single-threaded at the moment. And this means that we can't use the full potential of the CPU on modern computers. So instead, I ended up doing a first start with a very low level API. And the idea was to, once it's mature enough, I could offer to integrate it as a backend in other libraries, and disable, for example, multi-threading if that is not a desirable feature to have. So that way we can get consistent performance for the in algebra, and we can have the convenient API that they already provide. So for the users, there won't be much of a change once the experimental API is integrated, but it'll offer significantly better performance. So next, I'm going to talk about the optimizations that I use in various parts of the library and how they affect the performance of the operations on matrices. So the core part of the library, I would say, is matrix multiplication, because effectively everything else depends on it. Like the triangular solve uses matrix multiplication under the hood, so does the Cholesky decomposition, and so on. And all of this is based on Kazushige Goto's work for matrix multiplication and the Bliss analytical model, with some minor tweaks to account for differences between CPUs, like ARC64 versus x86, or Intel CPUs versus AMD CPUs. The first step is to handle special cases, the common ones like matrix times matrix, vector times matrix, or matrix times vector, and vector times vector, whether it's an inner or outer product. And when you have a matrix times matrix at a high level, what you want to do is you want to chunk your matrix into blocks that fit into each level of the cache on your CPU. So you have 3 levels typically, the L1, L2, and L3. So you want a big chunk to fit into L3 cache, and then smaller chunks to fit into L2 and L1 that you keep reusing. So that way the code is written in a way that makes the most use of the CPU cache. And at the low level, you want to multiply these blocks with each other. And for that, we use multiple vectorized kernels for small rank updates. So these are basically a lot of small matrix multiplications that are performed sequentially, or if you enable multi-threading, are parallelized with Rayon. So like it was discussed in the previous talk, but Rayon was a joy to work with in Rust, and it's extremely efficient after comparing it with OpenMP and Intel One API. So Rayon can also be used to parallelize computations and achieves very high performance competitive with like either matching or exceeding the established libraries such as Eigen and MKL, as well as OpenBlast. Next up, I'm going to speak about how I optimize the matrix decompositions. So the matrix decompositions typically fall into two camps. There's the unblocked decompositions, which are the ones that operate on the matrix column by column and row by row. And then there's the blocked decompositions, which operate on the matrix in chunks. So for the unblocked decompositions, I'm taking as an example the LU decomposition with full pivoting. So the idea is to decompose our matrix into a product of two triangular matrices, L and U. So L is lower triangular and U is upper triangular. And such that their product is equal to the matrix modulo row and column permutations. The way the algorithm works at the high level is you want to find the pivot in the matrix. The pivot is simply the largest element in the matrix in absolute value. You permute the matrix so that this element is in the top left corner. You perform a rank update using the first row and column of the matrix to the trailing submatrix, and then you repeat everything with the trailing submatrix. So you move one row and column at a time. Since we only operate on one column at a time, the algorithm is memory bound since you have to access the matrix each iteration. So the number of flops is roughly equal to the number of memory accesses. And because of that, there's a crucial observation that we can make here, which is that we traverse the matrix twice per iteration. So we traverse it the first time when we want to find the pivot, and then a second time when we want to update the trailing submatrix. And with that observation in mind, we can rewrite the algorithm in this way. So we assume the pivot is known. So if it's the first iteration, we just compute the pivot as usual, but after that, we assume it is known. We permute the matrix so that the pivot is the deleted element. And then instead of doing the update and the pivot searched in two steps, we fuse them in one step. So we update the matrix and simultaneously keep track of the largest element in absolute value. And then we save that value and use it as a pivot for the next iteration. As far as I know, this idea has not been used in other libraries, but it offers a significant speed up without losing any of the stability properties. So the algorithm is effectively exactly the same, but you get up to 2 times speed up because you only traverse the matrix once in a memory bound algorithm. There are other optimizations that are also used, like using CMD instructions to further speed up the decomposition. So here, the code is very complex. So I'm not going to go through all of it, but if you want to see it, I linked the GitHub in the slide. The idea is that you want to perform multiple optimizations. So for example, instead of doing the update and the pivot selection one step at a time, you want to use a vector register to process multiple elements at the same time. And you also want to use instruction level parallelism, or otherwise called manual loop unrolling. So instead of using one register to process the matrix per iteration, you use 2 to 4 registers, basically as many as you can fit in the CPU without having to spill to the stack. And there's also thread level parallelism. So basically you split the matrix into multiple chunks, perform the update and compute the pivot for each chunk. And then at the end, you aggregate all the results together. So this is all the same algorithm as in algebra, but it is almost 6 times faster on a single thread and 13 times faster with multiple threads, which is a huge speed up compared to the classic techniques. So this is part of the SIMD code that I talked about earlier. I'm not going to go through all of it, but you can see here that I have a for loop that is raced through the matrix and the column that we update by. And we perform first the update of the column, and then in the second step, we find the pivot, which here is found using the best value function, which is not shown here. But basically, it compares the absolute value and then stores the index corresponding to it. And then at the very end, we aggregate the results. So that's it for the LU decomposition. Next up, I'll be moving to an example of the blocked matrix decompositions. So I'm going to take the Cholesky decomposition as an example. And the idea is that you want to split your matrix. Well, first of all, to explain what the Cholesky decomposition is, basically you have a symmetric positive definite matrix A, and you want to find a triangular matrix L such that A is equal to L times L transpose. So the algorithm recursively splits A and L into 4 sections: top left, top right, bottom left, and bottom right. If you write the formulas down, you can find that the top left of the Cholesky decomposition is just the Cholesky decomposition of the top left corner. And then for the bottom left part, you do a triangular solve. And then for the bottom right part, you again perform a rank down date and then do another Cholesky decomposition. So here, the only non-recursive step is the triangular solve. So most of the time is spent there. And for small matrices, you fall back to the block algorithm. So since most of the time is spent in the triangular solve, you don't have to use very fancy optimizations. You can simply rely on the matrix multiplication to carry the algorithm and ensure that it achieves very high performance. So there aren't many fancy optimizations, but thanks to the work we did in the matrix multiplication part, we get performance that's very competitive with the state of the art. Next up, for the eigenvalue solvers, typically these are split into 2 steps. So the first step is reducing the matrix to a condensed form. So a condensed form is either a bidiagonal matrix for the SVD, a tridiagonal matrix for the Hermitian EVD, and a Hessenberg matrix for the non-Hermitian EVD. So these use various techniques that were actually also used by, explained by the Bliss team. And the idea is to fuse the kernels rather than instead of working with the algorithm at a high level, you try to fuse multiple steps at the same time. So this is a generalized form of what we showcase for the LU. And of course, there's also like factorization and multi-threading, which are always useful for this kind of, which are less useful for the algorithm since it's more memory bound, but it still offers a significant benefit compared to just performing the algorithm sequentially. And then the phase 2 is performing the actual decomposition. So for the SVT and the Hermitian AVT, we use divide and conquer methods. This is very convenient since we can divide the algorithm into 2 steps. So these can be processed in parallel using Rayon again. And once their decompositions are computed, you have to fuse the merge results together. So this is done partly sequentially and partly in parallel when we have to do the matrix multiplications. And finally, for the non-Hermitian EVD, the algorithm is a lot more complex. And it is based on the QR algorithm. So this is what is used in LAPACK and TLAPACK, which is a port of LAPACK to C++. And the idea is to take the traditional QR algorithm and use it with multiple shifts at the same time. Unfortunately, I don't think I could explain the entire algorithm during this talk, so that will be left for another time, hopefully. Now for the benchmarks. I wanted to show I can't show the benchmarks for all the algorithms in the library since there's too many, but they are on the website if you want to take a look. So the algorithms for the LU, the Cholesky, and the SVD look roughly the same. For small matrices, you have n algebra, which is very competitive for small matrices. And then as the matrix size grows, you start to benefit more and more from the blocking and the parallelization. So for the LU, and this is the unblocked LU, you have the for very large matrices, you have fair being the leading contender even without parallelizing the computations thanks to the kernel fusion. And once you add parallelism, you gain a two times speed up for large matrices. For the Cholesky, you have about the same. Here we added in the array since LAPACK offers the Cholesky decomposition. So LAPACK performance is somewhat inconsistent because again, you can't control how it you don't have fine control over the multi-threading. So if I set it to be multi-threaded, you get very inconsistent performance because it tries to use multiple threads even for very small matrices, which adds a significant overhead. But it becomes more and more competitive as the matrix size grows. And here we can see that even for large matrices, and even with single-threaded performance, we are still very competitive with other libraries. And once you add multi-thread into the mix, the gap gets even bigger. Lastly, for the SVD, here, and algebra actually remains competitive for quite a while for matrices up to about a size of 50. And this is due to the fact that it uses the QR algorithm, which is very efficient for small matrices. Sorry for the SVD. Yeah, it uses the QR algorithm, whereas faer currently only uses the divide and conquer algorithm, which is not very efficient for small matrices. So here we suffer quite a bit for small matrices. But again, as the matrix size grows, we become very competitive. And even with a single thread, we managed to achieve what other libraries have to use all the cores in the CPU to get that kind of performance. So what is next for the library? Right now, you'll notice that I haven't shown many snippets of code. And the reason behind that is that the library is actually very low level and not very convenient to use. Basically, it doesn't allocate any memory internally, so it asks the user to allocate their own memory. And it also has very extensive options for the precision you want for the eigenvalue decompositions, for example. And the number of threads you want to use is handled on a per call basis. So every function call ends up being very verbose. So ideally, I would like to work on a high-level API that can be more accessible for users, and it can offer the same kind of performance without having to pay as much attention to all the steps in the algorithm, while still allowing like an escape hatch so that users can use the low-level API if they want to get even more performance. Other than that, there also have been plans to integrate faer as an experimental backend in algebra. So this is something I want to dedicate some of my time to see it flourish, because this way the users get the best of both worlds. So they get an API that they are already used to with the very high performance that I showcased. And hopefully this can help the ecosystem this can help the ecosystem grow even more and establish us as a very important competitor in the domain of high performance computing. In the future, I would also like to work on two main things, which are the banded matrix algorithms. So a banded matrix is a matrix which is sparse, like it's all zeros except for a band around the diagonal. We can typically use this structure to speed up a lot of the algorithms that I talked about. And eventually, I would also like to move on to sparse matrix compositions, which are in very high demand for things like the physics simulations, where you want to exploit the sparsity of your system, because usually it is far too large to be treated as a dense matrix. And it is also used in quadratic programming solvers. So this is something that I would like there are already various implementations for the simple shell sparse matrix decompositions, which are the sparse equivalent of the unblocked decompositions. But there are very, very few supernodal decompositions. There is, for example, sweet sparse and UMF-back, which are well known, but they are not very convenient to use, as there are, as far as I know, no real Rust wrappers for them. And the techniques behind them are not very often talked about. So I would like to see if I can port some of their ideas to Rust and see if we can have a flourishing ecosystem of sparse linear algebra in addition to dense linear algebra. So that's it for the talk. If there are any questions, I'll be here to respond for the next few minutes.
Brilliant. Thank you very much, Sarah, for that talk. So we have a few questions starting to come in. If anyone else has questions, open up the Q&A box, start typing them in. A good idea for the Q&A box, which Miguel has already had, is to start putting the name of the speaker you're asking the question to, especially as we're moving to shorter talks, and there's going to be speakers in a very short amount of time. If you just write Sarah : and then your question, we'll know which speaker your question is for, which will matter shortly when we have some shorter talks, and the questions will start getting mixed up. So I'm going to take some questions from the chat, and then Sarah can respond to any else via text we don't have time for. So one question we have is related to something you mentioned at the end, which is banded, sparse and blocked matrices. And the question is, what are the most awkward parts of trying to design an API for these kind of structured matrices that may be distributed and or you want to run on GPUs? And does Rust lend itself well to such a design space?
So for banded matrices, typically they are stored as dense matrices, dense rectangular matrices that only represent the part around the diagonal. So that is something that could be handled with faer, the same way it is handled in NumPy, for example. Like my idea for banded matrices is to basically copy the NumPy API. For blocked matrices, I'm not sure how to best handle those. Something I tried to work on in the past without much success, because it ends up being very problem dependent. Like typically you have like a lot of when you have a block matrix, you want to exploit the different structures inside each block. So for example, sometimes you have triangular blocks or diagonal blocks, and you want to use this as well. Or you can have sparse blocks and dense blocks together, and you want to mix and match, which gets very hard to handle in at the library level. And it's something that is best handled at the moment, but on a per application basis. For sparse matrices, I'm not yet sure about how to design the API. I've heard good things about MATLAB, for example, and my plan is to take a look into how they do things, and ideally try to do something that is similar to that, since as far as I know, MATLAB is the standard for sparse linear algebra. And as for the GPU, I'm not quite sure yet how to handle this part since, as you mentioned, for parallelism, there's rayon on the CPU, but on the GPU, there's not really a single framework that is well established at the moment. So I haven't tried to investigate it very deeply. But for the CPU, I believe Rust is a very good option for all of those algorithms. So for sparse bandit and block matrices, I believe Rust is right. I believe Rust is one of the best options we can have for linear algebra if you're doing library work at least, and you want to achieve robustness without having, for example, having to deal with segmentation faults or data races.